Hello, my name is James Lee, and today I'll be presenting the paper TimeConvNets, a deep time windowed convolution neural network design for real-time video facial expression recognition. Both me and Alexander Wong belong to the Department of Systems Design Engineering at the VIP lab at the University of Waterloo. We'd like to begin with a quick introduction as to why facial expression recognition is important. It serves two main purposes: understanding emotional states and also picking up conversational cues. If you look at the graph, research has shown that up to 55% of the information conveyed by a spoken message is actually expressed by the visual aspect alone, with the words only taking up 37%. Unfortunately, people who suffer from autism spectrum disorder often also have an impaired ability to infer emotions based on facial expressions, which can lead to loneliness and depression due to increased difficulties interacting with other people. To tackle this problem, first, knowing the two main types of facial expression classification is important. In the single static image case, a single label is assigned to each individual image frame. This type of classification often has a fast training and inference speed, but lacks the inclusion of spatial temporal characteristics. However, in the dynamic video case, a single label is assigned to an entire video sequence. This type of classification is able to capture important spatial temporal information, but often suffers from a much slower training speed and inference time. When designing a system to help these individuals with autism spectrum disorder, low latency is key, as we need to provide real-time feedback for a seamless societal interaction. Also, as facial expressions are of a transient nature, consisting of an onset, peak, and offset phase, this spatial temporal information is key for also accurately classifying the onset and offset phases. Traditional 2D CNNs are not designed to capture temporal characteristics. We propose the idea of using sliding temporal windows, which are T-frame video subsequences stacked along the channel dimension, in order to balance the low computational complexity of single image classification with the high accuracy of leveraging temporal information. TimeConvNets are able to encode both spatial and temporal information in a very efficient manner with the use of these sliding temporal windows. The flow of the TimeConvNet is as such. Given a subsequent stack, in this case of 5 frames, it is stacked in the channel dimension and passed through a convolutional spatial temporal encoding layer. Then, the data is passed through a backbone architecture where the predicted class is generated after a softmax. Every good system requires a good dataset as well in order to function properly. Designed for the purpose of training TimeConvNet specifically, we created BigFaceX, a novel dataset which was created by modifying and aggregating 3 publicly available video datasets: CK+, BOM1, and Interface. BigFaceX was created like so. Unique sequences are extracted, cropped to their facial bounding boxes, and then resized to 48 by 48 pixels. After stacking these frames in the channel dimension, they're then added to BigFaceX, where they're labeled with the same label as the original video. We tested our TimeConvNets using 3 different backbone architectures: mini-exception, ResNet20, and MobileNet v2. We compare the results against a vanilla 2D mini-exception, a ResNet20 leveraging 3D convolution, and a ResNet20 leveraging 2+1D convolution. As shown, we can see that each of the TimeConvNets strikes a different balance between accuracy, inference speed, and number of parameters. For example, we can see that the TimeConvNet leveraging the mini-exception backbone has the fastest inference time out of them all, but actually has the lowest accuracy out of all the TimeConvNets. For MobileNet v2, we can see that it has a good balance between accuracy and inference time, but actually has 2 million parameters, which is an order of magnitude more than the other two. In this paper, we presented TimeConvNets, which are able to encode spatial temporal information in an efficient manner, and show 3 different models showcasing different balances of accuracy, inference speed, and number of parameters. We also presented BigFaceX, a novel dataset tailored specifically for time-windowed learning. The use cases of an accurate real-time facial expression classifier also extend beyond assisting people with autism spectrum disorder, and can also help in fields such as driver state monitoring, depression detection, customer reactions in marketing, ambient interfaces, and so on. Thank you very much for listening.